In this video, we're going to address the question of how to find the inverse of a function algebraically. Let's begin by recalling how inverse functions work in general. It's true of any function whatsoever that it will assign exactly one output to any given input, but we say that a function f is invertible if it's also the case that for every output there is exactly one input. If a function f is invertible, then it will have a corresponding inverse function denoted f inverse. And this inverse function is basically defined by the property that if f of x equals y, then f inverse of y must equal x. We might also express this in a little diagram that shows the exact same thing. If the function f takes x to y, then the function f inverse must take y to x. And recall that contemplating this diagram reveals two important identities involving a function and its inverse. Indeed, if we apply the function f to x, then it will take us to y, and then applying the function f inverse to that will take us right back to x. Or, going the other way around, f inverse will take some element to x, and then applying f will return us right back to that same input. In other words, the composition of a function with its own inverse, in either order, must just give us the original input right back. And recall that geometrically we can tell whether a function is invertible by checking to see whether it passes the horizontal line test. And if it does, then we can produce the graph of the inverse of that function simply by reflecting the graph of the function across the diagonal y equals x. All of these things are very important to understand, but they still leave one question unaddressed, which is the question, how can we find inverse functions algebraically? Imagine, for instance, that we're not given the graph of a function, but that a function is presented to us simply in terms of an algebraic expression. Can we check, using algebra alone, whether that function is invertible? And if so, can we also produce an algebraic expression that defines the inverse function? That's the question we'd like to consider next. As you may have guessed, the answer to that question is yes. So let's try to take a look at how that works by considering a very simple example, namely the example of the function f of x equals x plus 1. Our goal here is to come up with a formula that defines the inverse of the function f, provided, of course, that that inverse exists. And our first step will simply be to rewrite the function as y equals x plus 1, thereby replacing the notation f of x with a dependent variable y, as we often do when working with functions. Now here's the idea. The function f takes x values and sends them to y values. So the inverse function would have to take y values and send them to x values. But the expression that we're working with presents y as a function of x. So to produce the inverse function, we would like to present the variable x as a function of y. The way to proceed is therefore simply to solve our equation for x. And we begin just by reversing or swapping the two sides of the equation. Then we subtract 1 from both sides to write x as a function of y. And since x equals f inverse of y, we immediately arrive at a formula for the inverse function. F inverse of y equals y minus 1. The final step is simply to rename the variable x, since when working with functions on the real line, it's customary to present the independent variable as x. And so the final form that our answer will take will be f inverse of x equals x minus 1. And this also makes sense from an intuitive point of view. Indeed, the function f takes a real number x and adds 1 to it, so the inverse function should take a real number x and subtract 1 from it. Indeed, we can also verify directly that our answer makes sense just by composing it with the function f. And sure enough, the composition of f and f inverse, as we've defined them, will just give us x as required. Let's try to apply this method to a more difficult problem. So this example is asking us to find the inverse of the function defined by the formula 1 plus the cube root of x all raised to the power 7. And what we'll do is begin by writing this with the variable y in place of f of x. So we'll just say y is equal to 1 plus the cube root of x, all raised to the power 7. This presents the variable y as a function of x, and what we want to do is present x as a function of y. So we want to solve for x here. We can begin by raising both sides to the power 1 over 7, or taking the 7th root of both sides. Next, let's subtract 1 from both sides of our equation. So we'll have the 7th root of y minus 1 equals the cube root of x. Finally, we will cube both sides. So this will be the 7th root of y minus 1 cubed equals x. At this stage, we have isolated x, and we can therefore say that the inverse function, f inverse, will be defined by this expression involving y. And we'll just replace the variable y with x now, so that we have a final form for the inverse function. And this would be our answer. A couple things to point out here is that we can check that our answer makes sense simply by composing it with the original function f and verifying that the result is equal to x. This is always a good way to check whether your answer makes sense and is correct. Another thing worth pointing out is that in taking steps in our calculation, we always applied operations like taking the 7th root or cubing both sides that were themselves invertible operations. This ensures that nothing was lost along the way and that our function actually is invertible. Let's have a look at one more example. Here too we're being asked to find the inverse of a certain function that's defined by an algebraic formula. In this case, the formula 1 all over 1 plus x to the 4th. We would begin using our general method by rewriting f of x as the dependent variable y, and then attempting to solve for x. How do we solve for x here? Well, we can begin by multiplying both sides of the equation by the denominator 1 plus x to the 4th. So that would give us 1 plus x to the 4th times y equals 1. Then we could divide both sides by y to obtain 1 plus x to the power 4th equals 1 over y. We could subtract 1 from both sides to obtain x to the power 4 equals 1 over y minus 1. And then, to isolate x, what we would need to do is take the 4th root of both sides. But it's at this point that we actually have to stop and be careful, because taking the 4th root is not an invertible operation. Indeed, think back to your knowledge of roots and radicals and recall that when taking the 4th root, or any even root of an expression, there's a choice to be made. We could take the principal square root, right, which is the positive 4th root of 1 over y minus 1, or we could take the negative 4th root of 1 over y minus 1. Since there is not a unique way to solve for x here, we must actually conclude that the function f is not invertible. The moral of the story here is that when trying to find the inverse of a function algebraically, try to make sure that every step in your work is also an invertible operation. To conclude, there's one subtlety that I think is worth pointing out. Let's ask ourselves the question, are the functions x squared and radical x inverses of one another? At first glance, it may seem like the answer should be yes, because squaring a number and taking the square root are inverse operations, or at least that's how it seems to be. But take a look at the graphs of these two functions, which look roughly like the curves shown here. It now seems like the answer to the question must be no, because indeed, the blue curve which corresponds to the function f of x equals x squared, clearly fails the horizontal line test, and therefore cannot be invertible. On the other hand, notice that if we forget about the values of f at negative numbers and restrict its domain to just numbers that are greater than or equal to 0, then it suddenly does pass the horizontal line test and does become an invertible function. Moreover, the restriction of f to non-negative numbers has an inverse which is precisely equal to g of x, or radical x. This highlights a subtle point, namely that even though a function may not be invertible over its entire domain, it may become invertible if its domain is restricted. Algebraically, this would play out, for our particular example, as follows. If we were to try to solve the equation y equals x squared for x, then we would have to make a choice. We would either take the principal square root and thereby end up with a function which is the inverse of f when f is restricted to non-negative numbers. Or we could take the negative square root and thereby end up with an inverse function which is the inverse of f when restricted to non-positive numbers.